Okay, so I was caught up in a traffic, that's what. So today we will continue our discussion about path vector routing. അപ്പോൾ കോളേജിൽ പോയി വരുന്ന വഴി ബ്ലോക്കായി, അങ്ങോട്ടും ബ്ലോക്ക് ഉണ്ടായിരുന്നു. So we discussed about three routing algorithms, that is distance vector, link state and path vector. First two, distance vector and link state, they are intra-domain routing algorithms, that is intra-autonomous system routing algorithms, and the path vector routing is inter-autonomous system routing algorithm. So or you say inter-domain routing algorithm. So we saw path vector routing yesterday, how path vector routing is done, how minimum spanning, best spanning tree, it's not the least cost tree, it's based on the policies. We'll see when we discuss border gateway protocol, which is using path vector routing in a modified form. So it's a very complex protocol, this border gateway protocol. So we are discussing routing protocols now, that's our topic. So we discussed about the internet structure. So we saw that there are backbones, these are private, these are not owned by any government, these are private carriers which say Tata, Luz and all such telecom companies, NTT, Docomo, all those people are serving the internet. So there are tier 1 players, tier 2 players, tier 3 players, ISPs, you can say. All of them are ISPs, they provide service, internet service. So we get internet service from some service provider which is either a tier 2 or a tier 3 operator. Okay, so that's the case here. So and there are peering points to for this backbones as well as service providers to exchange traffic among them. And then we'll see about say other aspects of this architecture later, but for the time being our problem is how to route traffic from, say, from this customer network to this customer network across this cloud, or you call it as internet. So that is done using routing routers, and routers use different algorithms to achieve that, and based on that you have different routing protocols. Three, we came to something is that we need hierarchical routing. Routing cannot be done using a single protocol. It has to be there could be some things which run at a higher level, at the autonomous system level, and something which will run at the lower level within the autonomous system. So among autonomous system there should be some routing protocol, and within the autonomous system there should be some routing protocol. That is what the hierarchy is. And we saw autonomous system numbers, the stub autonomous system, multi-homed autonomous system, and transient autonomous system. So transient allow traffic to pass through them, multi-homed do not allow traffic to pass through them, they are connected to more than one ISP, one provider networks. Okay, so other autonomous systems or other ISPs. So this is, and the stub ISP is connected, it's a terminal, like it's a terminal network, it's terminal autonomous system. It has no other connection to a second autonomous system, it is having connection to only one single autonomous system. So then routing protocols. So we'll take up routing protocol. We started with the routing information protocol, and routing information protocol, RIP, is the it's an intra-domain routing protocol. So it's an intra-domain routing protocol based on distance vector algorithm. If you remember distance vector routing algorithm, it is based on the concept that every router will periodically exchange information with its neighbors. Whatever it knows about its network, it will exchange with its neighbors. That is the basic idea. And here the cost, we need to define the routing cost. The routing cost here is mentioned as the hop count, so number of hops to reach from point A to point B. And RIP is specifically suited for smaller autonomous systems, say autonomous systems whose diameter is within 15 hops, that is 15 routers, radius could be 15 routers. If the hop is 16, it is the router is designated as unreachable. That is what the maximum is 15. So if you want a protocol which requires, if you have an autonomous system which has diameter more than 15 hops, you will go for open shortest path first routing protocol. So that is another variant that has a different metric for computing the cost. The cost is mentioned in terms of a different parameter there. Here it is hop count. There we'll assign an explicit cost based on all these parameters: delay, all bandwidth, all those things, performance, all those things that is mentioned there. But still, the admin is free to choose any cost metric as required. Okay, so 16 hop count is designated as unreachable. So and each of these routers will advertise. Adhan varna distance vector routing illa, each router will exchange whatever it knows. If you recollect this figure, I think I can go to a slide. Go to slide number 12. No, yeah, this is distance vector routing. So this is how I periodically send knowledge about the whole internet network to my neighbors. Whatever I know about the whole network, I'll send it to the neighbors. That is go to slide number 33. Right. So so this is I should put the slide numbers. Right. So you are talking about types of hop counts. So hop counts, here the hop count is considered the source network to the router, source router. This connection is not considered as a hop. You assume that that is without any cost. So to reach from network N1 to network N4, the hop required is 1, 2, say that is this hop 1, then 2 and 3 hops, that is 1, 2 and 3 hops, that is N1 to N2 and then N2 to N3 and N3 to N4. These 3 hops are required. So this is how you specify the hops. So your forwarding table in routing information protocol, in addition to the next router. So this is for the forwarding table for router 1. For router 1, the forwarding table will be saying that it has entries N1. To reach N1, the cost in hops is 1, right? That is for any destination, that's packet that is coming from this side. There will be obviously 1 hop involved, right? Then N2, 1 hop, right, towards the right. Then N3, the next router is R2. N3 reach R2 ആണ്. So the number of hops is, there is 1, 2 hops, that is 2 hops. Then N4, to reach N4 there is 1 hop here, second hop and the third hop, so 3. So you have 3 hops, so R2. So this is what do you say, the forwarding table for R1, router R1. Similarly for router R2 as well as R3. So each hop is assigned a unit cost in this example, right? So and you usually this RIP is run as a process in the application layer. It runs as a process in the application layer. If you recollect, this is a TCP/IP protocol suite, and the application layer, it runs as a process, and then it is passed on as a UDP. UDP is a protocol within this transport layer. TCP and UDP are dominant protocols in the transport layer, so it is passed on as a UDP datagram. So application layer will have some connection to the transport layer through some specific port. This process root daemon will have a process to this will have a port to this connection to this transport layer, and UDP datagram is generated. So RIP messages are encapsulated. If you recollect, in the first lectures we mentioned about encapsulation and decapsulation. OSI model la paranjathu. So it is encapsulated in a UDP datagram, and it is then encapsulated in IP. IP is the network layer thing. So internet data frame. We came across this thing. So it was included as a payload within this. So this is an application layer process, and it will generate a message related to what do you say, RIP, which is encapsulated in a UDP datagram, and it runs on UDP port 520, and this UDP datagram is then encapsulated in IPv4 data frame, IPv4 data frame. So, and that is what the encapsulation is shown here. This is the header part of the IPv4 data frame. We had this slide earlier. In IPv4 data frame എന്ന് പറഞ്ഞ ഒരു lecture സ്ലൈഡിലാണ്, അവിടെ നിന്ന് ഞാൻ എടുത്താണ് ഈ ഒരു പോർഷൻ, just to show the relation. So, and then it is sent to the physical layer. Physical layer, it's all a data link layer. All we discussed data link layer, flow control, error control, all those things are there, and finally it's sent as bits to the destination. So application layer process is generating a message. It is encapsulated in UDP datagram in the transport layer, and then passed on to the network layer, where it is further encapsulated in the IP datagram and then sent. There are two versions of RIP. The one is RIP version 1 and the other is version 2. Two versions of routing information protocol. So there is the dominant one as of now, whatever is used is RIP v2 version 2. There are two types of messages. One is a request message, other one is a response message. So request message is that when a router, maybe a router had a downtime, it was off, it was some repair or something, and it just came up, it is turned on, and then it has it doesn't know idea about what is there around, about its neighbors, so it will send a greeting packet of sort. That is called as the request message. Then timeout entries, we will discuss that. Timeout in the sense that if you specify a route within the routing table, the forwarding table, you will turn on a timer. So after a specific number of seconds, duration, say I think it's 180 seconds, the entry will time out unless it is updated. So again, so periodically there is, the routing tables are very dynamic, so you have to the entries might have timed out. So anyway, in other case, the router will try to gain updates about the network. So that is a request message. It will seek updates from its neighbors. So, and the response message is sent out by the neighbors who receive this request message. It can be two things. Either it could be solicited response message. That means in response to your request message, you can send an information. So I might ask the router B, say in this example, say after the router 2 might send a request to router 1 and router 3, see, tell me what is the status. So they will tell what they know, that is I am able to connect to network 4, network 3, and this router will tell I am able to connect to network 1 and network 2, my immediate router is this, that. So that message is obtained. That is the solicited response. Unsolicited is happening periodically, every 30 seconds or so. So it's a randomly set actually, 25 to 35 seconds. അതിനകത്ത് റാൻഡം ആയിട്ടാണ് ഓരോ റൂട്ടേഴ്സും ഈ unsolicited messages ചെയ്യുന്നത്. Otherwise all the routers will simultaneously try to send a response message. So unsolicited responses. So that is also set, the timer is set randomly. It's not fixed at 30 seconds. It's at periodic intervals. So this is the RIP message format. So if you see, this is it's whether it's a command or command. It's a request or a response, 1 or 2, that is a field. Then the version is version RIPv2, version 2, family, TCP IP. So you are using the TCP IP protocol, that's why version is 2. Then tag all those things about you to have information about the ASN number, everything. Network address is the destination address. Then the subnet mask. So we'll come back to this. We have discussed this CIDR, classless interdomain routing, and basically all these concepts will become clear when you look at the larger picture. We discussed a topic which is called as route aggregation or address aggregation. Say it's like ഞാനൊരു എക്സാമ്പിൾ പറഞ്ഞു. ഇപ്പോൾ ബാലരാമപുരത്ത് പോകാനുള്ള ഒരു ആൾ എറണാകുളത്ത് നിന്ന് പുറപ്പെടുകയാണ്. Say he won't ask from Ernakulam where is Balarampapuram. He'll say it's in Trivandrum. So same way, depending upon you'll use the CIDR notation, slash notation, and here whatever the prefix, it says it is Asianet, this is Kerala Vision, this is Geo. It is all the traffic with the prefix will be routed to that ISP. So the routing tables can be at the higher level, can be kept smaller. So that is route aggregation. So this is to serve all those things. Okay, this is to serve for all these things. And network address, destination address, subnet mask, all those things. Basically, even though these are RIP, routing information protocol, these are intra-domain routing protocols. They are to get updated from the inter-domain routing protocol. A BGP is a border gateway protocol, which we will discuss later. It is a inter-autonomous system routing protocol, but it will also have at the end of the task of updating the inter-autonomous system communication, it will make entries which will be used to update the inner routers, interior routers. So the picture will become clear at the end of this session, at the end of this topics when we discuss BGP. Anyway, as of now, all those these are understood. Distance, number of hops to the destination. So this is this would be repeated. This could be repeated at periodic intervals. This is what is repeated at 30 seconds intervals. Now it is same as the distance vector routing algorithm. So what it does is that this is your network here. This is your network here. So and you have a router 1, router 2, router 3 and a router 4. This is cut type. Router 4 cut type. Network nokige. Network there is network 1 connect 2, network 3. This is a transient network, transit. So anyway, when it is booted up, all these we don't have a situation where all the routers are turned on simultaneously, but this is a very fictional situation where all the routers are turned on simultaneously and they don't know anything. Okay, next router they don't know, they don't have any idea. Initialized as 1, it has to get an update now. It has to get update. So what it does is that this is the initial table, routing table, forwarding table of router R1. Now R2 will exchange its, if you remember, R2 is this router. R2 will give its routing table to R1. Similarly, R1 will also exchange its routing table to R2. This happens. So here we are seeing a case where R2 is exchanging tables with its neighbors. That's what the case is saying. So it will send its whole response. So R1 is asking, what is the what information do you have about the network? So it is sending a response. It's sending a message telling what do you have, what is the status of the network. So and it is having a blank table. Here it finds that from R2's table it gets new information that N4 and N5 could be reached through R2, and the cost involved will be 2, because I have 1 hop to R2 and then the next cost, the cost involved is 2. So there is the update, that is what happening there. Here, yes, someone turned on the mic. Hello. എന്താണ് ഡൗട്ട് ആണോ? കേട്ടില്ല. സമയം തീരാറായി. സമയം തീരാറായി. ഓ കുഴപ്പമില്ല. റൈറ്റ്, ഇറ്റ്സ് ഓക്കെ. So this is say in this case similarly R2 is exchanging a stable to R3. Here also there is an update taking place. There are two so you will change the next router address. This is the next router address. You will just update. This is an update which is done. This is the arbitrary edukana. So it will retain the initial contents wherever it is the least cost. The new information is added. That is the approach. So say, but there are some exceptions. There are some exceptions if you take ഇപ്പോൾ ഒരു റൂട്ട് അറിയാം, ബട്ട് വരുന്ന റൂട്ടിന് ഇൻഫിനിറ്റ് വാല്യൂ ഇട്ടിട്ടുണ്ടെന്ന ഒരു കേസ് വരാം. എന്ന് പറഞ്ഞാൽ ലിങ്ക് ബ്രേക്ക് ചെയ്തൊരു കേസ് വരാം. അങ്ങനെ 3 സിറ്റുവേഷൻസാണ് നമ്മൾ നോക്കുന്നത്. It will select the routes as a new ones except in these 3 cases. So it will retain, except other than these 3 cases, it will retain the old routes. It will retain the old routes. So that is the situation. So what happens is that say if your received route it does not exist in this table, so it is added. That is what the situation is here. The cost of the received route is lower than the cost of the old one, then the received route should be selected. Least cost routing ആണല്ലോ. So cost കുറവാണെങ്കിൽ ആഡ് ചെയ്യണം. അങ്ങനെ ഒരു സിറ്റുവേഷൻ ഇവിടെ കാണിച്ചിട്ടില്ല, ബിക്കോസ് ഇവിടെ എല്ലാം ഇനീഷ്യൽ കോസ്റ്റ് 2 തന്നെയായിരുന്നു. ഇനി if the cost of the received route is higher than the cost of the whole old one, but the value of the next router is same, this situation is also not shown here. For instance, I will just give an example for this. അതായത് നമ്മളുടെ ഈ ഒരു റൂട്ടർ R1 say after boot time and after several seconds into this process, R1 knows that it could reach say some network through R2, but all on a sudden say network R5 N5 through R2, but this link fails. Now R2 gets to know that this link has failed and it will put an infinite value to this link. So R2ന് R1 നേരത്തെ അറിഞ്ഞിരുന്നതെന്ന് വെച്ചാൽ R2 വഴി N5 എത്താൻ വേണ്ടി 2 ഹോപ്പ്, 1 so it required 2 hops. So that is what its update. It knew that it required 2 hops. Now R2 is now becoming aware that this link has failed and it is given an update that is an infinite cost. Now when R1 sees the routing table from R2, it doesn't get confused, because I already have a least cost of 2 to this, but R2 is telling that I have it's unreachable. 16 ആണ്, ഹോപ്പ് 16 ആണ്, ഹോപ്പ് നമ്പർ 16 ഇടും. അപ്പോൾ അത് it is understood that it's an infinite, unreachable ആണ്. There is some failure in this link. This particular link has failed. So what it does is that it will add that value 16 to its routing table. That is what is mentioned here. So if the cost of the received route is higher than the cost of the old one, but the value of the next router is same in both the routes, the received route should be selected as a new one. That is the assumption. That is a safeguard to prevent situation like that is say least cost പെട്ടെന്ന് propagate ചെയ്യും. So count to infinity problem prevent ചെയ്യാൻ വേണ്ടി ഒരു സൊല്യൂഷനാണ്. Say network failures link failures will not reflect faster. That is why this solution is done. Yes, we'll stop. I have next class. That's another reason. Otherwise I would have summed up these 3 things. I'll just finish it off. Okay, so there are 3 timers. One is a periodic timer. That is what it is. I told it is every router advertises every 30 seconds. It is actually 25 and 30 seconds. It's set randomly. All routers at random intervals it will just update this particular thing, this particular event. Unsolicited response messages are sent at 25 to 30 seconds hour duration ലായിരിക്കും സെറ്റ് ചെയ്യുന്നത്. Then expiration timer is, I mentioned about the route timer. Route will time out after 180 seconds. So it will be set infinite value, destination is unreachable. Okay, say we'll just disperse for the day. Okay, we'll disperse for the day.